Well, the beginning of a new chapter, chapter 6, higher degree polynomial and rational functions. So what we're going to do is go beyond what we have done in the past. What we've done so far are linear functions, which look like that, where the exponents on the x and y are 1. Then we went to quadratic functions. That look like that, and remember these make a parallelogram, makes a parabola. And this time we're going to go into some higher order or higher degree polynomials, maybe like negative 6x to the 4th power minus 10x cubed minus 4x squared, those kind, where the degree of the polynomial, which is the highest exponent of the polynomial, is going to be a number greater than 2. All right, I like going into these new chapters because it just kind of gives us new direction. I get a little bit tired of doing the same old thing, so when we get into a new chapter, it's always fun and exciting. Yeah, I'm being facetious there as far as fun and exciting. I mean, since when is college algebra fun and exciting, right? But anyway, when you get started with this section, I would like you to peruse, glance, study, whatever you need to do, the algebra toolbox when it has to do with polynomials and factoring higher degree polynomials, rational expressions, and all of that. And I know it's a little bit long to go through here, but it is really good to have a reminder of what's going on. And I guess I would really encourage you to look bottom of page 425, where they're giving you long division of polynomials, which is real painful, but I will give you a really fast and easy way to divide polynomials later in the course that is not nearly as painful as, for instance, example number 12. So anyway, we'll get started with 6.1, higher degree polynomial functions. And again, these higher degree polynomial functions are equations that have a degree higher than 2, or an exponent higher than 2. So we're going to start out with cubic functions. And if you look at the figures on page 429, left-hand column, it gives you some cubic function pictures, what the graph looks like. And starting with A, that is pretty much what a cubic function looks like. Now remember, a while back I gave you a page that had a bunch of the different function pictures in there, and I think there is one in this book, if I remember right. It's on page 432, and it gives you an idea of what some of these functions look like, but we'll get to that shortly. So we're going to start out with cubic functions. They're all going to take this shape of like that. They may take this shape, and that all depends on if the lead coefficient is a positive or a negative number. And I say lead coefficient. What I mean by that is this number positive or negative? The first coefficient, when you put them in descending order of the exponent, or if I say the lead coefficient or the coefficient in front of the highest degree, or the higher degree, which is going to be the highest exponent there, that is going to give you this shape. If it's positive, it's going to give you that shape there. So just kind of gives you an idea of what the shape's going to look like, what direction it's going to go, and just some things to keep track of is again, the specific behavior, or the specific end behavior. We're going to talk quite a bit about end behavior. The end behavior is what goes on either end of the graph. So here and here, what's going on there? Okay, that's end behavior. This stuff in here that we're talking about, okay, that's got another name, and we'll get to that later, but it's pretty much the local points, but we'll, again, talk about that in a minute. So, the graph of a quadratic function, which is one that has a 2 as the highest exponent, it's a parabola, and that parabola has a turning point. Okay, it's going to turn at some point here at the vertex. So it may be decreasing until we get to here, and then it will start increasing. So there's one turning point. So we have x squared plus 3x plus 2, and that's our function, and it has one turning point. When we get to x cubes, we're going to have more than one turning point. But again, I don't want to start going too fast. I want to kind of stay in line with what the book's saying on page 429. Recall that the graph of a quadratic function is a parabola with one turning point called the vertex, and that vertex is a maximum point or a minimum. In this case, it's a minimum point. Notice that in each of the graphs of the cubic third-degree functions shown in figures 6.2b and c, there are 2 points where the function changes from increasing or decreasing to increasing. So, for example, there are 2 places. It increases and there's a turning point. Decreases, there's a turning point. Okay, so there's 2 places here. There's a maximum of 2 places. There doesn't have to be 2 places, as what is that? 6.2 shows, as A shows, because see where it goes like this? Okay, it didn't really turn from increasing to decreasing. It just didn't increase as much, and then it went to increasing again. So anyway, these turning points are called local extrema points of the graph of the function. Local extrema points. Okay, so that's what those turning points are. In particular, a point where the curve changes from decreasing. Let me get my graph back up here. Where a curve changes from decreasing to increasing. So maybe it's going like this, and then it goes like this, and then it goes like this. So this part here, where it goes from decreasing to increasing, is called the local minimum point, right there. And where it goes from increasing to decreasing, that point there is called the local maximum point, because obviously it's at the maximum. This is the minimum. Now it's called local because this is not the highest point of the graph. You get over here, you get on the ends here, in behavior does different things. So see, this continues to go up. So it goes above the max. But locally here, kind of where things happen in the graph, things change. We have a maximum and a minimum. What goes on down here, you're assuming nothing is going to change. It's just going to go into infinity negative. This is going to go into infinity positive as far as the y value, and negative as far as the x value. But locally here, where things are changing, this is the minimum, the local minimum point, and this is the local maximum point. Okay? So, in general, a cubic equation will have 0 or 2 local extrema points. Okay, so this one has 2. This one here, let me draw another graph that's similar to A, has 0. Because again, it goes up, but it doesn't, we don't have a maximum local point because it doesn't come back down. It just kind of evens out and then goes back up again. So there are 0 minimum or maximum points there. Okay, so we can have 0 or 2 for a cubic function. The highest point on the graph over an interval is called the absolute maximum point, and obviously the lowest point on the graph over an interval is called the absolute minimum point. Okay, so the absolute minimum, absolute maximum are strictly based on an interval. So if I'm saying, let's look at this interval right here, between those 2 points, we have an absolute maximum point. Okay, so if they tell us that we're only interested in this part of the graph between these 2 lines, then we know we have an absolute maximum and no absolute minimum there. Unless we want to call this point here maybe the absolute minimum point, but that will depend on what we're doing here in the equation. All right, so let's look at example 1 and try to tie some of the stuff together. All right, so it says graph y equals x cubed minus 27x. Okay, so you can use your graphing calculator in order to find this out without any problem, or you can just do some basic algebra and figure it out using algebra that way. But then it says find the local maximum and local minimum, if possible. And that local maximum and minimum are going to be -3 and 54. And that'll be my maximum. My minimum will be +3 and -54. But again, that all has to do with using your graphing calculator and putting that graph y equals x cubed minus 27x in there. Look at the graph that it gives you on your calculator to find the max and the min. And then where is the absolute maximum of this function on the interval 0, 3. Okay, so there, B, they're asking the local maximum and local minimum. C, they're saying the absolute maximum based on an interval. Okay, so when you are given the interval 0, 3, then you know that that absolute maximum is at y equals 0, x equals 0. Okay, it has to be there because we're only given, now let me put the graph in here. We go up here, we go back down through the origin, and then we go back up here through 5. But we're only interested in 0, 3. So we're interested in all the numbers including 0 and 3 here. Okay, so when we're only given 0 and 3, the highest point here is going to be, the highest point in this part of the graph is going to be right there at 0, 0. Okay, so we're y equals 0 and x equals 0. So that's all they're asking for there. Example 2, they're talking about elderly workers, and again, you're using your graphing calculator here, and they give you a formula. You plug in your numbers from the data, the year, and then the elderly workforce, and it tells you which window, or where to put your window at 0, 100 and at 0, 12, and then go ahead and answer the other questions that they have there. All right, so I'm going to stop there before we go into quartic functions and start with 6.1b.